Hello, my name is Hope Brown, and today I'm going to be presenting my project on making photoactive bioplastics using metal coordination. I would like to thank the Department of Chemistry and Center for Photochemical Sciences at Bowling Green State University, as well as the Center for Undergraduate Research. The main goal of the project was to create a robust, environmentally friendly plastic-like material using metal coordination to biopolymers. If you look at the first image, you'll see a circle with a V5 plus on it. This is a vanadium 5 plus ion, and this was mixed with chitosan, which is the pink molecule, as well as pectin, which was the blue molecule. These were combined to produce the yellow film, which is a vanadium film. Below that, you'll see a CO2 plus inside a circle. That is a cobalt 2 plus ion, and this was once again mixed with chitosan, the pink structure, and pectin, the blue structure, to produce a pink cobalt 2 plus film. Why is this important? The Earth and its oceans are highly polluted with plastics and microplastics. I'm sure you've all heard the research and the studies about how we need to limit our plastic use. By using these natural polymers, microplastic pollution is significantly lessened. Using coordination of metal ions can help strengthen the plastic, which can then be used for more applications, and it's still degradable with light. My work with the vanadium bioplastics are inspired by our findings from our group previously, Kalani, and her work on vanadium's photoresponse. So if you look at the first photo, you'll see a vanadium 5 cluster, and this can be reduced to a vanadium 4 cluster as well as produce carbon dioxide. Now, this reaction is reversible. With oxygen added back in, it can once again become a vanadium 5 cluster. My work is also inspired by the chitosan pectin films made by Hoagland and Paris. And if you look at my second image, you will see a chitosan pectin glycerol film with no metal ion. The film is completely clear, and the metal ions are what add in that color. So without a metal ion, the plastic is completely clear. So how do I make the metal coordination biopolymers and their films? The films were made using vanadium as the metal ion and then pectin, chitosan, and glycerol as the biopolymers. So chitosan, pectin, and glycerol were heated and mixed, and then poured into a film mold and air dried for 72 hours. After this 72 hours, the dry films were then soaked in 20 millimolars of sodium metavanadate for 5 minutes. After the 5 minutes, the films were left to air dry for another 48 hours. After that 48 hours, I was able to test the pH, water stability, the strength of the films, as well as the photo response of the films. The vanadium 5 chitosan pectin films are stable in water with a pH of 2 through 11. So if you look at the first image, you'll see the before soaking. I have pHs of 2.27, 3.13, 6.40, 8.83, 10.30, 11.30, and 12.32. You'll also see the films prior to soaking. The next photo you'll see is immediately after soaking. So if you'll look, you'll see that pH 2 through 11.3 all are very stable. There's no leaching of color into the water. At pH 12, you start to see the water begin to turn yellow, and that's the vanadium ion leaching into the water and leaving the film. After 24 hours, I came back to the films. 2 through 11 still held their color and still were films. The 12.32 pH film had completely degraded. So therefore, the pH study proves that the films degrade in water with a pH of over 11. The vanadium metal ions also make the films photoresponsive. So if you look at the first picture, you'll see the vanadium yellow film. There is nothing that's been done to it yet. This is before it's been irradiated, before any light has touched it. You'll also see our very cool BGSU emblem. So the film was then irradiated for a couple of hours. You can see where the emblem was at. You can see how there's still a very pigmented yellow portion that was not irradiated, covered by the emblem. You can also see that Everything that was not covered by the emblem is a nice deep green, light blue color. That's the photoactive of the vanadium metal ions. After 24 hours of irradiation, the film begins to turn a very dark blue, almost black color, but you can still see where the emblem is at and where some of the vanadium has not been irradiated. So this color change and the ability to pattern the films with the emblem after being irradiated demonstrates that the vanadium metal ions in the films are photoactive. The color change is what proves that it's photoactive. So the color change in the films during irradiation is confirmed with diffuse reflectance. Diffuse reflectance shows that as you irradiate, the films absorb the longer wavelength light. So if you look at the chart, you'll see many different colors. And what does this mean? All of the colors below that black, very deep blue line, those are what the film absorbs. What's reflected, what color you see the film producing, is that deep blue black color. That one is higher than all of the other ones. This shows that that's what it's reflecting and all the others it absorbs. So diffuse reflectance shows us that this is consistent with the color change we see during light irradiation. I was also able to take SEM characterization photos, and you can see that in the first photo, there are many cracks, crevices, lots of pores. The second photo after irradiation, there are still a lot of those pores. There's still a lot of cracks. They're just slightly smoothed over. However, there's no real structural changes through these photos. The structure is still the same. So I also was able to test that the irradiated films are not as strong as the non-irradiated films. If you'll look at the first set of photos, you'll see films irradiated at 0 minutes through 60 minutes and their color change. The next set of photos will show you the weight on the films. So the first photo shows you 50 grams on a dry, non-irradiated film. I was able to measure from where the film sat with no weight on it to how it sat with weight on it. And there was a 3 millimeter difference from no weight with 50 grams for the dry non-irradiated film. On the dry irradiated film, it was 4 millimeters lower than how it originally sat without the 50-gram weight. So the dry irradiated film sits lower than the dry non-irradiated film. And this means that that irradiated film is weaker than the non-irradiated film. So my conclusions and future work. The films are very stable in water, acidic, neutral, and basic solutions, up to a pH of 11.3. But they're not stable in very basic solutions, so a pH of 12 and above. The films do swell in water, but they're still stable. The color change in the films during irradiation can be confirmed with diffuse reflectance. So as we saw before, the films were able to change colors as they were irradiated, and the graph of diffuse reflectance showed us exactly what color they should be reflecting. The SEM images prove that there are no big structural changes in the vanadium chitoxanthectin films with irradiation. So we saw some of the cracks were smoothed over, but we didn't see any of them in different positions than what they were originally. This means that when vanadium is irradiated, there's no structural changes from vanadium 5 to vanadium 4. The next steps for my project are to continue making and testing materials with different metal ions and natural polysaccharides. So as you saw in the first slide, I have been making films with cobalt 2+. I also plan to make films with metals such as copper and nickel, and I will be trying different polysaccharides such as chitoxanthectin without glycerol, gum arabic, and a few others. I would like to acknowledge my group members, Karina Haddad and Kalani Ederisingi. My work was also supported by the BGSU Department of Chemistry, BGSU Center for Undergraduate Research, the NSF Career, and the ACS Herman Frasch Foundation. Thank you all so much for watching my presentation. I very much appreciate it. Please let me know if you have any questions. Again, thank you all.